Okay, so we now we want to analyze the insertion sort. So basically, we want to analyze the time complexity of insertion sort. How much is the run time for insertion sort? So just to recap, for insertion sort, what we are doing, we have a sorted we have an array which is the input A1 to AN. This is the A array. So we have this code for j is equal to 2 to n. So we are putting this key as aj and I are pointing to j minus 1, and now we have a while loop while I is greater than 0, and this key is, if the key is less than ai, then we have to do something, and that is basically ai plus 1 is greater than ai, and then we are doing I is equal to I minus 1. So this is 1, 2, 3, 4, 5, 6 and 7. We are just putting a I plus 1 is equal to key. So this is the code for insertion sort, and we have seen the runtime will depend on the size of the input. It will depend on n. So that's why we parameterize by n. So this is the runtime for n input. Okay, for size of the input in n, and then we have seen the input will depend on the runtime will depend on the pattern of the input. So if we have a already sorted array, then it will take less time than if we have a reverse sorted array, it will take more time. So this is the type of, so this is the types of analysis. 3 types of analysis we will do. First one is worst case. That means Tn is the maximum, it is guaranteed maximum time for maximum time our code is taking for any input, for any input of size n. So we fix n, that is why it is Tn. We fix n. If we fix n, then this worst case is the Tn is the maximum time. So what is the maximum time our code is taking? So we so that is the worst case. So for insertion sort, when is the worst case? Insertion sort worst case is if the input is reverse sorted, then it is taking maximum time, because in that case, so for insertion sort, worst case is if the input is reverse sorted. So that means if we have say numbers say 9, 7, 6, 4, 3, 2, 1, if this is the input, suppose this is the input, we want to run this insertion sort on this input. So what it will, so everybody has to come forward. So the j is pointing here. So then this is getter. So 9 will come here, 7 will come here. So everybody will come forward. So everybody has to come forward. So that is the maximum time it will take. There is no other input which can give the more runtime than this. So this is sort of guarantee. So we are having maximum this time. So this is sort of guarantee. Okay, and this is good, because if we say I have a sorting algorithm and maximum my worst case runtime is this much. So that means nobody, that is the worst case, means that is the maximum time my algo is taking. So that means nobody will nobody cannot come with some input where my code is performing bad than that what I am claiming as a worst case. So that is the reason worst case is the most usual analysis one must do for any algorithm. Okay. And the best case is, then the next one is best case. which is called bogus also, because it is a cheating. So, this is the best case. So, this is best case means the Tn is minimum time it is taking, minimum time to sort. I mean, this is a sorting algorithm, insertion sort we are talking about. Minimum time our algo is taking for a input of size n, minimum time to sort n numbers. This is the best case. So, this is the minimum time. So, for insertion sort, when is the best case will occur? If the input is already sorted. So, if the input is already sorted, that means what? That means if we have input like this, say 3, 5, 6, 9, 10, 12, 13. This is already sorted input. So, for this input, if we run the insertion sort, then how much time we will spend? We just start with j is this. Now, this is greater than this. We do not, so only one comparison. Then j is here, only one comparison. J, so, I will be here, j is here. So, only one. Then j is pointing here. Now, this will be I. Then this is our key. Then we compare this. So, only one comparison again. So, j is pointing here, I is pointing here, only one. So, this is the best case, because just every for we are just scanning that we are just reading the array and only one comparison is occurring. So, this is the best case scenario. So, this is the minimum time our algorithm is taking. There is no other input which can be lesser runtime than this. Okay. So, but the thing is, but this is only for, I mean, this best case is happening for insertion sort if the array is already sorted. Now, which case you want to be usually do, best case or worst case? So, that is very crucial point. So, best case means it is not guaranteed. I mean, see, suppose Microsoft open a competition and ask this group to have to build a sorting algorithm, ask this group to build a sorting algorithm. Now, you build a sorting algorithm and you build a sorting algorithm, you submit to the Microsoft, and Microsoft give your code to this group and your code to other group and ask to find out the input where it is performing bad. Now, you are telling that my worst case runtime is this, worst case it is taking this much time, and you are telling, hey Microsoft, my best case runtime is this, but you have to run this for this type of input. For this type of input I am getting best case. You are not telling the guarantee one, you are not guaranteeing that your runtime cannot go beyond this, you are telling your best case. That means, for this type of input your code is good, but they are telling my code is worst case runtime is this. That means, whatever input you can have, you cannot go beyond this runtime, your runtime cannot be more than this. So, that is sort of guarantee. So, but if you tell only best case, then anybody can, the adversary can come with some input where your code is performing bad, because you are only highlighting your best case. So, that is why this is sort of, this is bogus, this is sort of cheating. So, we will not go for, so people not prefer to do this analysis, because this is for some certain input, whereas this worst case is the usual analysis we will do, because this is the guarantee one, it is guaranteed. So, we can guarantee that our code is, our algorithm is taking this much time. And there is third one is average case analysis. So, this is the another one, average case analysis, average case. So, average case means, so on an average how much time it is taking, we know the worst case, we know the best case. Worst case is for certain input, best case is certain input. Now, if we, so this is the Tn is the average runtime, average time. That means for average, to be very honest, we need to take the expectation. So, maybe we need to deal with the expected value of Tn is how much. So, there we need to talk about, we need to assume some distribution on the input. Input is following equally likely or something. So, maybe we will do some type of analysis in our course, but this is basically average case, expected runtime. Okay. So, this is the three types of analysis one can think of any algorithm. Worst case is the maximum time for any input, best case is the minimum time for certain input, minimum time which is occurring for certain input, and the average case is the on an average or expected runtime. Okay. Now, suppose we want to do the, so we know the worst case is the usual analysis one must go for. Now, suppose we want to do worst case analysis of insertion sort. So, we want to do the worst case of insertion sort. Okay. Suppose Tn is the worst case runtime, worst case runtime for insertion sort. So, worst case means, so what we fix? We fix n is fixed. Suppose we are talking about, we have say 100 input, we are sorting 100 input, and since it is worst case for insertion sort, the input is reverse sorted. So, we fix these two information, input is reverse sorted. So, this two is fixed. We fix the size of the input, that is say 100, we are sorting 100 element, and the inputs are in the reverse sorted way. So, that is why it is giving us the worst case. Now, tell me, if we fix these two situation, will it runtime depend, will the runtime depend on any other thing? Any other factor will be interfering in the runtime. So, that is a crucial question. Any other factor will depend, will be, so this then the runtime will depend on what? Any other factor? We already fix n. So, Tn is, we already fixed the worst case. So, the input is reverse sorted. Then after that, will it depend on any other thing? Suppose you are running this on your brand new laptop, code do processor, and you are running this same code, a reverse sorted input, input size is fixed. On a computer, old computer, your grandfather is, or grandfather is having. So, which will take faster? Your PC, your laptop will take faster time. So, your laptop can give the output in a second, but our grandfather computer can take 1 hour to give the output. So, it will depend on the speed of the computer where we are running, speed of our PC where we are running the code. Now, it is depending on the computer where we are running the code. Now, then how will judge whether two code is good, which one is good? Suppose you have a sorting code, they have a sorting code. So, now how to judge whichever is good? Now, we have to run this code in the same computer. Not only that, we have to run this in the same computer, in the same situation, in the same time. That is not possible. So, if I am running your code in daytime, where this sun is from, this is a summer time and it is very hot time, and this we do not have AC in the room, and our PC is taking some time to adjust the fan, all these things. So, your computer will, I mean, and their code we are running in the night time. So, it is very difficult to run two pieces of code in the same environment, in the same situation. So, that is a headache. I mean, it is not possible. Every time if our computer is multi user, every time some processor is running something. So, it is very difficult to run, it is very difficult to get two similar situation of a workstation. So, that is a botheration. So, then how we can judge two piece of code, whichever is faster than whichever is slower, that is very difficult to judge in this way, because we cannot give the same identical situation of this PC where we are running this code. Okay. And so that is really a botheration. So, to avoid this botheration, what we need to bring, which is called asymptotic notation. Asymptotic notation, which is a very big idea. I mean, it is a great idea where we can get rid of from the computer, from the machine dependencies. Okay. Now, where from this idea is coming? Suppose we have two code, one is having runtime this, say n cube plus n plus 3 or 2n cube plus 5n plus 3, and we have another piece of code which is say 100n square plus 50n plus 9, this many seconds. Okay. So, how we get this? We just get we have a, say for example, insertion sort. We know the we have how many loops we know. So, insertion sort we have a outer loop, say j is equal to 2 to n, and then key we are assigning to this, and I is equal to j minus 1, and then we have a for loop, I is greater than 0 and the key is less than ai. Then we have ai plus 1 is greater than ai, and then we are decreasing I by 1, and then finally here we are assigning a I plus 1 is equal to key. So, this is the piece of code for insertion sort. Now, these are basically coming how much time we are spending for this assigning, how much we are add for this compare, how much time we are comparing. So, it depends on the machine. So, how much our machine is, our architecture, our hardware is taking for this operation. So, our adder, our multiplexer, all these things. So, these are all machine dependent terms, and this n and these are coming from these loops. Okay. So, suppose we have a sorting algorithm with this is the runtime for our machine, for a machine, and this is the runtime for another machine. Okay. Now, can you tell me which code is better? Because these factors are coming, how much time we are spending in doing this assignment, doing this comparison, how much our computer is taking for that. So, these machine dependent terms. Now, if you draw this curve, if you draw this true curve in terms of n, suppose this is n and this is the runtime Tn. So, one curve will be like this and another curve will be like this. So, after certain point of time n0, so this will be our what? This will be our T2 and this will be our T1. So, you see, as we take n large, then T2 looks better, but if we take n small, then because of this factor it is looking T1 is better, but if we make n large, then it is clear that T2 is better. T2 is better runtime, right? Because the growth. So, we want to see the growth. So, that is why we need to bring this asymptotic notation. So, asymptotic notation in the sense what we do in the engineering sense, we ignore all the lower order term, then we ignore the leading coefficient. This will give us the what is called big theta. We will formally define this big theta, and then again we do the same thing, we will ignore the lower order term. This is, so this is better than this. So, that means we want to see the growth of this runtime as n tending to infinity. So, as n tending to infinity, as n is large, then we will get rid of from this mesh independent term, because these are mesh independent terms. These are the terms how much time we are spending to compare two number in our machine. So, the adder, multiplexer, all these terms, we do not care about that, because it is very difficult to get an identical situation for a machine. So, that is why we do not bother how much time we are spending here. So, this is we are just following, this is a constant time, this is basically we are following, this is theta of 1 time, because we do not care this is how many second, 5 second, 4 second, but this is some constant work we are doing in terms of n, because this we just assigning this one assignment and one assignment here. So, this is basically theta of 1, some constant amount of time. That constant is nothing not related to n, that constant is the time our computer will take. Now, if it is our brand new machine, it will take less time, if it is our grandfather machine, it will take more time. But why should we bother about the machine we are running the code? We want to get rid of from this mesh independent things. So, that is why we just talk about this is the constant time, theta of 1 time. It may be 10 second, it may be 5 second, it may be millisecond for a brand new computer, but we do not care about that. We will just think that this is the constant time, theta of 1 time. This is some c, some constant, theta of 1 time. So, this is the big idea, this asymptotic notion. So, now we have a method to compare two piece of code without depending on the machine. Otherwise, we have to run this code into two machine in an identical situation, then we check the exact time how much they are spending, exact time how much this code is spending, then if it is spending 10 second, if it is spending 10.5 second, we said this code is better. But that also difficult, because we need to have the identical situation, identical condition of these two machine. So, that is why this is the best way, this is the very useful way, this is the very useful way to compare two code in a asymptotic sense. That means, we want to see the growth of the runtime, we want to see when n is large, when the input size is large tending to infinity, where the runtime is going. So, that is the observation we will do for asymptotic notation. And so, in the asymptotic sense, we will see that this time. So, this is a loop for, this is a loop in n, and this is a loop depending on how much we are coming there, but there this is the time basically we are spending constant time, some constant time. So, this will write in theta of 1 way. Okay. So, now we formally define the asymptotic notation. We have three asymptotic notation, one is big theta, we just now we have said, another one is big O, another one is big omega, mainly three notation we use. So, they have mathematical definition are there. So, this is the definition. Okay, so, we define the big theta. So, big theta of f of n. So, it is basically a set of all function g of n such that it is bounded by c of f of n less than equal to g of n less than equal to c2 of f of n. Okay. And for all n after sub, because we do not care about the low n, because we want to see the growth of this this runtime. So, we want to take this is to be greater than some as n tending to infinity where it is going. Okay. And where C1 and C2 are two positive constant. Two positive constant. So, for example, then big theta of n square, if f n is n square, then it is basically set of all function g n such that we must have two constants such that C1 n square less than equal to g of n less than equal to C2 of n square for some n after some n0 and C1 C2 are two positive constant. So, for example, if we have say 10 n square plus 5. So, this is belongs to order of n square, because for this we can always choose C2 for some n and we can always choose C1 for some n, so that it will be bounded by both sides. Okay. Similarly, say 50 n square minus 5 n plus 3, this is also belongs to theta of n square, but we will be floppy, we do not write belongs to, you will just write this is theta of n square. Okay. So, as you said in engineering sense, what we do, we just ignore all lower order term, we ignore the leading coefficient, and this is n square, this is theta of n square. So, this is the asymptotic notation of theta of big theta of n square. So, in the next class we will talk about another two asymptotic notation, what is big O and big omega. Thank you.